How did you get on with assignment 7? In this lecture, I'll say something about how to prove statements that involve quantifiers, which is true for almost all mathematical theorems. Universally quantified statements of the form, for all natural numbers n, some property a(n) holds, where the quantification is over all natural numbers, are often proved by a method known as induction. I'll explain the method of induction with some examples from number theory. Number theory is one of the most important branches of mathematics. It studies the properties of the natural numbers 1, 2, 3, etc. We'll look at some elementary parts of the subject in later lectures, but for now it provides good examples of induction proofs. But first, let's look at how we might prove an existence statement.
We want to prove there exists x such that a of x. The obvious way is to find an object A for which A of A. For example, to show that there's an irrational number, just prove that square root of 2 is irrational, which we did. Unfortunately, this doesn't always work. Sometimes we use indirect proofs. For example, I worked through that problem about the cubic equation, where we showed that there was a point on the x-axis where the curve crossed it, and hence that the cubic had a solution. We never found the solution, we just showed that one existed. Let me give you a really fascinating example of an indirect proof. I'm going to prove that there are irrationals r and s such that r to the power s is rational. That actually came up in assignment 7, if you remember, and I promised then that I would look at this later. Well, now is that later. The proof involves considering two cases. Case 1, if the square root of 2 raised to the power square root of 2 happens to be rational, we can take r and s both equal to square root of 2. Then, by the assumption that square root of 2 to the square root of 2 is rational, we've shown that there are numbers r and s which are irrational, with r to the power s rational. Well, if case 1 isn't the case, then we must be in case 2, which is where root 2 to the root 2 is irrational. In which case, take r equals square root of 2 to the square root of 2, and s equals square root of 2. And if we do that, then r to the power s is root 2 to the root 2 all to the root 2, which by the way that exponents work is root 2 to the power root 2 times root 2, which is root 2 squared, which is 2. And 2 is rational. So again, we've proved that there are irrationals r and s such that r to the power s is rational. Taken together, case 1 and case 2 prove the theorem. I really like this example. It's not just clever, but it's cute. And it's cute because of the way it works. We really don't know whether this number, root 2 to the root 2, is rational or irrational. It's probably irrational, actually, but the point is we don't need to answer that question. We just look at the two alternatives. If it does happen to be rational, seems weird, but if it does happen to be rational, then we can find irrationals r and s with r to the s rational this way. On the other hand, if root 2 to the root 2 is irrational, which probably is the case, but again, we don't need to know that, then we take r to be this number, s to be that number, and then r to the s is 2, which is rational. So we don't know, officially, which one of these is the case, and more to the point, we don't need to prove which one of these is the case. We simply look at the two alternatives, and depending on which alternative we're in, we take different irrationals r and s, with r to the s being rational. So the choices of r and s are different in the two cases, but because these two cases exhaust all possibilities, this number is after all either rational or irrational, then this proves the result. By the way, this is known as the method of proof by cases. And it's a method that's used a lot in advanced mathematics. Pretty neat, huh? Well, now let's take a look at how we might prove a statement involving a universal quantifier. Suppose we wanted to prove a statement for all x, a of x. One way is to take an arbitrary x and show that it satisfies a of x. For example, to prove that for all n there is an m bigger than n squared, where the variables m and n range over the natural numbers. Well, this is a pretty trivial example, but I want to focus on the method that you would use to handle the two quantifiers in a statement like this, where in particular the first quantifier is a universal quantifier. Let n be an arbitrary natural number. Set m equal to n squared plus 1. Then m is bigger than n squared. And this proves the statement, there is an m bigger than n squared. And it follows that the statement for all n there is an m bigger than n squared is true. Okay, well, as I said, this is pretty trivial. Let's just see what's going on in terms of the logical reasoning. You want to prove a statement involving two quantifiers of the form for all n there is an m bigger than n squared. What we're going to do is eliminate one quantifier by replacing it by an arbitrary natural number. Now, by arbitrary, I mean we make no assumptions at all other than the fact that it is a natural number. The argument will have to hold for any natural number whatsoever, because we're trying to show that this is true for all n. So we pick an arbitrary one. Then we carry out some reasoning to verify the rest of the formula. Okay, when we eliminate that for all n, we're trying to prove that there is an m bigger than n squared, which is this statement. Now, in this case, it's a trivial argument. We just square n, add 1, and let m be that number. So we explicitly find an m that satisfies this property. In practice, you're probably going to have to do a lot of work here. With a more significant example, there could be several lines or even pages of arguments involved at this stage. But the point is, you eliminate the first quantifier by picking an arbitrary n, then you carry out some reasoning to prove the rest of the formula, which is this thing here. And when you've done that, because the argument works for an arbitrary natural number, it follows that you've proved it in this form. The for all n has been handled by reasoning with an arbitrary natural number. So we've taken away one of the quantifiers, carried out some reasoning, and proved the result. But let me stress that this works because the n that we pick is arbitrary. Well, another approach would be to use the method of contradiction. To prove for all x a of x, assume not for all x a of x. This is equivalent to exists x not a of x. Well, let C be an object such that not a of C. Notice that this isn't an arbitrary object. It's a specific object, admittedly an object whose identity we may not know, that is guaranteed to exist by this. The point is to prove this universal statement, we began by assuming its negation. Its negation gives us an existential statement, and that tells us that there will be some object, a specific object, for which not a of C. Now we've got a starting point to carry out a proof to derive a contradiction. Now reason with C, together with the fact that not a of C, to derive a contradiction. Now the exact reasoning you use will depend upon what the statement A says. But the general pattern is this. You want to prove for all x a of x, and you're going to use contradiction. So you assume not for all x a of x. That's equivalent to exist x not a of x. And that tells you you can find an object, or at least you know that an object exists for which not a of C. And then, if you can, you reason with that object using the fact that not a of C to derive a contradiction. Okay, again, we'll see examples of this later on. I'm just giving you the general overview of the way these arguments work. So, as in the previous case, if this looks a little bit mysterious, it'll become clearer, I hope, when we look at some specific examples later. In fact, at this stage, you might want to look back at assignment 7 and see what was going on there in the light of what I've just said here. And before I let you go, let me give you a little quiz. Well, the correct answer is no. This is not a valid proof. The point is, picking a positive rational p arbitrarily is not the same as letting p be arbitrary. The choice of p may indeed be arbitrary, but once you've made it, you've got a specific p. And we've even said what it is. That's actually different from saying let p be arbitrary. An arbitrary choice of p leads to a specific p, which you may have chosen arbitrarily, but you might have been unfortunate in your choice. You might have chosen a p that just happens to make something happen without there being any specific reason. It's a subtle point, I know, but it's an important point, so you really need to sort this one out. Letting p be arbitrary is not the same as picking in an arbitrary fashion a specific p. The point is that p is specific. Its choice may have been arbitrary, but once you've made it, it's specific. In contrast, when you argue with an arbitrary p, you don't know anything about the p. You certainly wouldn't know that it was equal to 0.001 or whatever. You may need to think about that one a little bit longer, or talk it over with some of your colleagues. Now let's look at proof by induction. This is the special case where we're proving universal quantified statements where the quantifier ranges over the natural numbers. For example, suppose I want to prove that 1 plus 2 plus etc. 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 plus n equals a half n, n plus 1. So the sum of the first n natural numbers is a half times n plus 1. Well, if you're meeting this problem for the first time, a smart thing to do is to begin by checking the first few cases, just to see, first of all, to see if it's true for the first few cases, and to try and get a sense of what's going on. So, if n equals 1, what do we get? Well, then we've just got 1 here, and putting n equals 1 into the formula, we have a half times 1 times 1 plus 1, which is a half, times 1 times 2, which is 1, and indeed 1 equals 1. So it's true in the first case. In the second case, n equals 2, what do we have? We have 1 plus 2 is the left-hand side, equals, put n equals 2 here, we get a half times 2 times 2 plus 1, which is a half times 2 times 3, a half to, so we've got 3, and 1 plus 2 does equal 3. So the formula is correct for n equals 2. We might want to try n equals 3. What do we get then? We get 1 plus 2 plus 3 equals a half, 3 plus 1, which is a half, 3, 4, which is 6, which is correct. So the formula checks out for the first 3 cases, and we might want to do a couple more cases. But at least that gives us some sense of what's going on. By doing this, we understand what the formula, we understand what the equation's saying. Now, so far, this isn't a proof. This is just checking the first 3 cases.
In fact, you've got to be very careful about jumping to conclusions based on the first 3 or 4 cases. So let me just stress that. This is not a proof. Okay, let me stress it again. Beware of jumping to conclusions. And to drive this point home, let me give you an example where if you jump to conclusions, you'll come to the wrong conclusion. Consider the formula Pn equals n squared plus n plus 41. If you start working out values for this formula, you find something rather interesting. You find that all values of Pn for n equals 1, 2, 3, etc. are prime numbers. Well, not quite. That's true until you reach n equals 41. And when you get to 41, you find that P of 41 works out at 1681, which is 41 squared. So the first series of values for n equals 1, 2, 3, etc., all the way up to 41, which is well beyond the number of cases most people would try out by hand, you find you've got a prime number. But if that leads you to believe that this formula generates primes for every n, then you're going to be wrong, because when you get to n equals 41, it's no longer prime. This example, by the way, is due to the famous Swiss mathematician Leonhard Euler in 1772. And it's a cautionary tale telling us not to jump to conclusions based on numerical evidence. Nevertheless, it's always a good idea, or it's often a good idea, to begin looking at a problem by working out a few cases. Not only do you get an understanding of what the formula is about, but you can sometimes, when you work out a few cases, you can find a pattern. In this case, there actually isn't much of a pattern to find. You work out the values and you just get numbers, and it turns out that the first 40 of them are primes. But in this case, if you look at what's going on, after, even if you did maybe a couple more, n equals 4, n equals 5, you'd begin to see a pattern of what's going on, how the two parts of the formula are combining, what's happening to the half. The half is dividing into the second one here, the first one here, the second one there. And after you've done a few cases, you can often find a way of capitalizing on the pattern that's there in order to produce the proof that I'll show in a minute. So induction proofs can often be derived by looking at the first few cases, seeing what the pattern is when you start plugging the numbers in, and then actually building a correct, rigorous proof. Okay, so the next step now is to begin with this numerical evidence and our understanding of how the formula works in order to come up with a rigorous proof of the fact that this formula holds for every n. The method of induction depends on a principle known as the principle of mathematical induction. Okay, and here's what it says. Suppose you want to prove a statement for all n, a of n. Establish the following two statements. 1, a of 1. That's known as the initial case, or the initial step. 2, prove the following statement. For all n, for all natural numbers n, if a of n is true, then a of n plus 1 is true. That's known as the induction step. Now, intuitively, this gives the statement for all n, a of n as follows. By the initial step, step 1, a of 1. If we now apply the induction step in the special case where n equals 1, we have a of 1 by the initial step, and that yields a of n plus 1, which is a of 2.
So by 2, or by step 2, A of 1 yields A of 2. So from A of 1, we can conclude A of 2. Okay, we begin by proving the initial step. So if we've proved A of 1, then we know that one's true. We can now apply the induction step in the special case where n equals 1. And having proved this, if we have A of 1, we can conclude A of 2. Then we can do the same thing again. Once we've got A of 2, we can put the 2 in here and conclude A of 3. So by A of 2 and the induction step, we can conclude A of 3, etc., all the way through the natural numbers. So it's a little bit like taking a row of dominoes and you knock the first one down, and providing the dominoes are close enough so that when one gets knocked down, the next one gets knocked down, then once you start to topple the row of dominoes, the first one goes down, then the first one knocks down the second one knocks down the third one knocks down the fourth one knocks down the fifth one, and so on and so on and so on, all through the natural numbers. So you get a row of dominoes falling down. So this basically says knock the first domino down and put the dominoes close enough together so that when one falls, the next one falls. Okay, that intuitive explanation is fine as far as it goes, but that's certainly not a rigorous demonstration of this method. The fact that proving these two together does yield that universally quantified statement, that's actually quite a deep result of mathematics. Okay. And let me just stress that. You need an axiom or a principle to make this work, called the principle of mathematical induction. The principle of mathematical induction is what tells you that 1 and 2 above, steps 1 and 2 above, yield for all n A of n. Okay, now we have the method of induction laid out before us. I'll apply it in order to prove that identity that we looked at a moment ago about the sum of the first n natural numbers. So I'm going to prove a theorem now that for any natural number n, 1 plus 2 plus 3 plus yada 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 plus n is a half n plus 1. I'm calling it a theorem because I'm going to give a rigorous proof. I'm going to use the method of mathematical induction. And since one of the purposes of a proof is to explain why something is true, it's usually good form to indicate to the reader the method you're going to use. It orientates the reader to what's going to come next. And I'm using a standard method here, namely mathematical induction, so it's good form to indicate that that's the method I'm going to use. Well, I have to do two things. I have to show that this is true when n equals 1, and then I have to show that if it's true at n, it follows at n plus 1. So the first step is to say that for n equals 1, the identity reduces to, well, n equals 1 on the left-hand side, I've just got 1. Put n equals 1 on the right-hand side, I've got a half times 1 times 1 plus 1, which is a half times 1 times 2. And indeed, the left-hand side does equal the right-hand side. So that's true.
since both sides equal 1. So we've proved the first step. Incidentally, you may have noticed that I referred to this not as an equation, but as an identity. And the reason is that an equation is something that you solve to find the value of a variable, either x in the case of a real number equation, or n in the case of a natural number equation. But this isn't an equation that you solve for n. This is an identity. It's something, it tells you that the two sides are always equal. And we use the word identity to refer to an expression like this that claims or that states that two things are equal for all values of n. So these two sides are identically equal. So the correct terms are an identity for something like this, an equation for something that you solve. Having said that, like many mathematicians, in practice I'm sometimes not particular in the words I use. If you caught me talking to my colleagues, you might find me using the word equation where I mean identity, possibly even using the word identity where I mean equation, although that one's less likely. But strictly speaking, an equation is something you solve. An identity is something that states that two things are always equal. Okay, let's move ahead. We've proved that the result is true at n equals 1. The next step is the induction step. So I'm going to assume the identity holds for n, i.e. I'm going to assume 1 plus 2 plus n equals a half n plus 1. And let me note now, and I'll put this in brackets, I want to deduce 1 plus 2 plus plus n plus 1 equals a half n plus 1 n plus 1 plus 1. Okay, that's just a note for myself to indicate the target I'm aiming for. And the challenge now is to start with what I know and deduce where I want to get. Well, how can I get this from this? Well, one way would be to add n plus 1 to both sides of that identity, which means that I'd get the left-hand side here, and then hope that when I work out the right-hand side, having added n plus 1, I end up with this expression. Okay, so let's add n plus 1 to both sides of, let me call it star. So star is the identity I'm assuming. Let me add n plus 1 to both sides of that. That gives me 1 plus 2 plus n plus 1 is a half n plus 1 plus n plus 1. So I've now got the left-hand side of what I want to prove. I need to show that the right-hand side is the right-hand side of the thing I want to prove. So I need to show that that is the same as that. Well, let's just see what happens. I can take the half out as a common factor. So I've got a half into n plus 1 plus 2 into n plus 1. And that equals a half n squared plus n plus 2n plus 2, which is a half n squared plus 3n plus 2. And this factors. This is a half n plus 1 n plus 2. But that's the same as that. I can write it explicitly, if you like, as a half n plus 1 n plus 1 plus 1.
which is the identity with n plus 1 in place of n. Hence, by the principle of mathematical induction, the identity holds for all n. And we're done. We've proved the initial step, a simple matter of observation, and we've proved the induction step by a fairly simple algebraic argument. And that's it. That's mathematical induction in practice, where the correct answers are this one, and this one. If you check back at the description I gave of the method of induction, you shouldn't have any difficulty realizing why this is the correct answer, why this is the correct answer, and why this is the correct answer. So if you got any of these wrong, you definitely need to go back and look at the lecture again and make sure you really understand induction. It's a very important technique in mathematics. Well, let me give you another example of an induction proof now, and this time I'll lay out the proof in a way that makes explicit the connection between the argument I give and the description of induction I gave a moment ago. And the example I want to give is the following theorem. Well, calling it a theorem is actually a bit of a stretch, but here's what I'm going to show, that if x is a positive real number, then for any natural number n, 1 plus x to the n plus 1 is bigger than 1 plus n plus 1 x. Okay, this result is not going to set the mathematical world on fire, but it is a good example to illustrate the way mathematical induction works, and in particular to connect the argument that I'm going to use to the earlier description I gave for mathematical induction. So here's the proof. Well, I'm going to begin by stating the method I'm going to use. It's mathematical induction. Since one of the purposes of proofs is to explain why something is true, it's always a good idea to begin by stating the method you use. That orientates a reader to the argument that's about to come. And to connect it to the description I gave of induction before, I'm going to let A of n be the statement 1 plus x to the n plus 1 bigger than 1 plus n plus 1x. So by induction, I'm going to prove for all n, A of n. Well, the first step is to prove A of 1, and A of 1 is the statement 1 plus x squared is bigger than 1 plus 2 of x, plus 2x. We put n equals 1 here, we'll get 1 plus x squared greater than 1 plus 2x. Is this true? Well, the answer is yes. It's true by the binomial theorem, which tells us that 1 plus x squared is equal to 1 plus 2x plus x squared, which is bigger than 1 plus 2x, because x squared is strictly positive. Notice that x is positive, so in particular x is non-zero, hence x squared is strictly positive, hence we have a strictly positive term here, hence that expression is strictly bigger than 1 plus 2x. So A of 1 is true. The induction step involves proving for all n, an implies a n plus 1. Or how do we typically prove a statement like this? We pick an arbitrary n and prove an implies an plus 1. And how do we prove an implication like this? We assume the antecedent and deduce the consequent. Well, an is the statement 1 plus x to the n plus 1 greater than 1 plus n plus 1x. And an plus 1 is the statement 1 plus x to the n plus 2 is greater than 1 plus n plus 2x. So the induction step boils down to assuming this and deducing that from it. So I'm going to focus on this now, and I'm going to begin by looking at the first expression, 1 plus x to the n plus 2. In order to use the induction hypothesis, I'm going to pull out one of these terms and write that as 1 plus x times 1 plus x to the n plus 1. And by the induction hypothesis, 1 plus x to the n plus 1 is bigger than 1 plus n plus 1x. And that equals 1 plus n plus 1x plus x plus n plus 1x squared, which equals 1 plus I've got n plus 1x and another x, so altogether I've got n plus 2x plus n plus 1x squared. And this is positive, so that expression is strictly bigger than 1 plus n plus 2x. And that part of it, the part here connected with this, is this. In other words, this proves n plus 1. And the theorem follows by induction. Okay, I've laid this out in gory detail here, but my purpose was to connect the kind of argument that you give when you do an induction proof with the description of induction that I gave a moment ago in terms of predicates an. Okay, so this is, so what I've been doing here is really emphasizing how my earlier description of induction connects to an actual proof. If you take out all of the pedagogic stuff that I've put in here, you've really got a 2 or 3 line argument. I mean, it really boils down to that step and then this step here. Those are the 2 key steps of the induction proof. Okay, well, there we are. Let me summarize how induction works. You want to prove that some statement an is valid for all natural numbers n. You first prove a1. That's usually a matter of simple observation. The next step is give an algebraic argument to establish the conditional a of n yields a of n plus 1. Usually you assume a of n and then you deduce a of n plus 1 from it. And typically you do that by looking at the form of a of n plus 1, manipulating it into such a form that you can apply a of n in order to carry out an argument. In other words, reduce a of n plus 1 to a form where you can use a of n. In conclusion, by the principle of mathematical induction, this proves for all n a of n. Occasionally, you might have to work pretty hard to establish the first case. Generally, this step is easy, and this one is where you have to put in the effort. But neither of these 2 steps on their own constitutes an induction proof.
It's the whole package that constitutes induction. My illustration of induction as knocking over a row of dominoes, while it's intuitively helpful, obscures the fact that this principle of mathematical induction is actually a pretty deep principle of mathematics. The reason it's deep, by the way, is because this is talking about an infinite collection. It's talking about all of the natural numbers, and there are infinitely many of them. And the moment you start talking about infinity in mathematics, there are subtleties and complexities lurking on the wings. Incidentally, that's why we usually complete a proof by writing a sentence something like, by the principle of mathematical induction, the result follows. Because this is heavyweight. And it's usually good practice and a shrewd move to mention a heavyweight if there's a heavyweight in the room. Okay, well, that's induction. I'd better tell you about a fairly common variant of induction. We sometimes need to prove a statement of the form, for all n greater than or equal to n0 a of n, where n0 is some fixed number, 5 or 10 or 20 or 1,000,000 or something. In this case, the first step is to verify a of n0. A of 1 may not be true. In fact, it's usually the case that when we are trying to prove something of this form, the reason we have an n0 as the starting point is precisely because the result doesn't hold at the beginning. We have to go out somewhere through the natural numbers until the result starts to hold. General induction starts at 1. This variant starts at some point beyond 1. But other than that, the argument's essentially the same. In particular, the induction step is to prove for all n greater than or equal to n0, a of n implies a of n plus 1. In fact, the example of induction I want to give you next uses this variant of induction. And that example is part of a famous result of mathematics called the fundamental theorem of arithmetic. Here's the part of the fundamental theorem of arithmetic that I want to prove. And it's the following theorem. Every natural number greater than 1 is either prime or a product of primes. Now we have to use that variant of induction for this one because it's not true at n equals 1. The theorem only holds for n equal to 2 or more. In fact, 1 is the only number for which it doesn't hold. So we're only just in the variant. We just missed 1 point. But we have to start at n equals 2. In other words, the first step of the induction is going to involve looking at n equals 2, not n equals 1. But with that one change, it's going to be an induction proof. So proof will be by induction. Well, the induction statement an is, well, you might think it's going to be n is either prime or a product of primes. Okay, based on the examples we've seen so far, you might imagine that a of n, the induction statement, is that n is either prime or a product of primes. Well, that turns out not to be the case. That just doesn't work. We have to pick something else. And this is what we pick. For all m, if 2 is less than or equal to m is less than or equal to n, then m is either a prime or a product of primes. So the induction statement, a of n, talks about all the numbers between 2 and n being prime or products of primes. So it's a sort of cumulative statement, if you like. As we go up through the natural numbers, we iterate on the cumulative fact
of things being primes or product of primes. And the induction proof establishes that an is true for all n bigger than 1. So we have to start with the first step, namely n equals 2. A of 2 says what? Well, if n equals 2, there only is one m between 2 and n. So the universal quantifier here is essentially vacuous. I mean, it's just a special case. It's a degenerate case. There is just n equals 2. So this statement, when n equals 2, simply says 2 is either prime or a product of primes, which is true. 2 is a prime. Now we're going to assume A of n and deduce A of n plus 1. Well, A of n plus 1 is going to talk about all numbers m between 2 and n plus 1. So let's look at one of those m's. Let m be a natural number, 2 less than or equal to m, less than or equal to n plus 1. Well, if m is less than or equal to n plus 1, m is either less than or equal to n, or m is equal to n plus 1. If m is less than or equal to n, then by A of n, m is either a prime or a product of primes. The only other possibility is that m equals n plus 1. Well, if n plus 1 is prime, then m is prime. So what happens if m equals n plus 1 and n plus 1 is not prime? Then there are natural numbers pq such that 1 less than pq less than n plus 1 and n plus 1 equals pq. If n plus 1 is not prime, then it can be obtained as a product of two smaller numbers. Not being prime means you can find two smaller numbers whose product equals the number. Two smaller numbers other than 1, that is. So this is just a definition of not being prime. Well, since 2 less than or equal to p and q less than or equal to n, by an, p and q are either primes or products of primes. These two numbers p and q are less than n plus 1, so they're less than or equal to n. That means these numbers are m's that fit into the induction hypothesis. They're less than or equal to n, so by A of n, each of these is either a prime or a product of primes. But n plus 1 is a product of them. So n plus 1 is a product of two numbers, each of which is either a prime or a product of primes. Hence n plus 1 is a product of primes. The theorem follows by induction. If you look back through this proof now, you'll see why we took our induction statement to be this somewhat more complicated looking statement. We wanted the induction statement to talk about all the numbers up to and including n being either prime or products of primes, so that when we went through the proof and we came down to a pair of numbers like this, we could immediately apply the induction hypothesis A of n in order to conclude that each of those two were either prime or products of primes, and therefore that the n plus 1 was either a prime or a product of primes. Incidentally, formulating induction statements that are cumulative in this fashion is quite common. It's often the case that in induction proofs you end up dropping down to some number or some pair or group of numbers smaller than the one you've got, and needing to apply the induction hypothesis to those smaller numbers, as we did here with P and Q. Okay, how did you like that one?
Okay, so now you know about induction. And with induction, we're starting to get into some serious university-level mathematics. Though the general idea is simple enough, if you can always go one more step, then you will eventually reach every natural number. In practice, it can require a lot of effort and ingenuity to construct an induction proof. See how you get on with assignment 8.